Welcome to Friday Happy Math Hour. Today's topic that I'm going to cover is basic matrix operations and inverses. Okay, now this, what I'm going to cover today, again, it goes back to section 6.4 to 6.5 or 6.6. Okay, so this is what I'm going to cover today. Matrix operations, which is real life examples. Determine dimensions of a matrix, which is a size. Matrix addition, matrix subtraction, scalar multiplication, and applications problems. And then for the second part, is going to be matrix multiplication, identity matrix, and inverse matrices. Okay, so let's begin with example number 1. It says matrices are important in the fields of management, natural science, engineering, and social science as a way to organize data. For example, this is furniture manufacturing. The Easy Life company manufactures sofas, armchairs, and 3 models, models A, B, and C. The company has regional warehouses in New York, Chicago, and San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B sofas, and 5 Model C sofas, and 15 Model A chairs, 20 Model A B chairs, and 8 Model C chairs to each warehouse. Okay? So now, this data might be organized by listing them as follows. Okay, here are the sofas, 10 Model A's, 12 Model B's, and 5 Model C's. And here are the chairs, 15 Model A's, 20 Model B's, and 8 Model C. This is called the tabulated data. You see, it can be done something like this, like an invoice. Or it can also be put as a matrix. Okay. Say matrix M for manufacturing. This is 10, 12, 10, 12, 5, and 15, 28. If you notice, this is a matrix. The rows is going to be the furniture, right, which is the sofas and the chairs. And the columns are going to be the models. Column refers to models A, B, and C. This is Model A, Model B, and Model C. And the first row is the sofas, and the second row are your chairs. So in this section or the this chapter, that's how they organize information into a matrix. Okay. Okay. Now matrices. Matrices are denoted. Say, for example, this is matrix A, and these are going to be like the elements. Okay. Uppercase letters are used to name matrices. Example, matrix A and matrix B, right? This is matrix A on the left, and this is matrix B to the right of matrix A. And the small letters or the lowercase letters are going to be the elements of the matrix. Okay, for example, this is A11, A12, A blank blank, right? Because the first number are the rows, and the second number is the columns. Okay, so for example, here matrix A. Again, these are my rows, right? And these are my columns. So for example, this is called the position of an element. A11 means, this means, right, a lowercase letter means this comes from matrix A. And this is the element or the position. This means the first row, first column. A14 means first row, column 4. A23 means second row, third column. Okay, on this one. Okay, what is the position of the following elements? Hey guys, please put in the chat if you know the answer, okay? What's A13? Anybody? What number is A13? Anybody knows? A13?
Isn't it 3?
The answer is 3. Very good, because this is the first row and third column. Very good. The answer is 3. How about 824? What do you guys think?
8.
The answer is going to be 8, right? Because it is a second row and fourth column, so the answer is 8. These are called the positions of the elements in a matrix. Okay, now comes the dimensions. The dimensions are the size. It's always going to be the rows times the columns. Okay, rows by columns. For example, on this example here, it says determine the order of the matrix, right? The order or the size means the same thing. There's 2 rows and 4 columns, so the dimensions are 2 by 4. Example 2, determine the dimensions of the matrices. Hey guys, what do you think, this matrix is? What would it be? You guys can put it in the chat if you want. Yes, Patricia, very good. It's a 3 by 3, right? How about the one in the middle? What will be the size of it? How many rows are there? 1, 2, 3. How many columns? 1 column. So this is a 3 by 1 matrix. The last example, right? How many rows are there? There's only 1 row. How many columns? 1, 2, 3. So this will be a 1. Okay. Determine the order of the matrix. How many rows here? We got 1, 2, 3, 4. So it's going to be a 4 by how many columns? 1, 2 columns. So it's a 4 by 2. Hey guys, it's very important to know the size of matrices, because when you do operation on matrices like add, subtract, and multiply, you have to know the size. Okay? So let me show you an example of what I'm talking about right now. For example, this is matrix A and matrix B. In order to add or subtract matrices, the matrices must be the same size. Okay, example, if you have A plus B, right, I'm going to add these two here. A plus B means the position of A11 will be added to B11. The position of A12 will be added to B12, right? So these are the elements that you're going to be adding. And in a similar fashion, A13 plus B13 and so forth, all the way until you end onto the size of the matrix. Then you begin doing the same thing on the second row. A21 plus B21, A22 plus B22, and you keep going until the very end here of the matrix. And then you do the third column, right, all the way to the nth column or to the nth column. And you keep doing the same thing until you add all the entries on the matrix. Okay. It's better to do an example with actual numbers. But anyway, guys, matrix addition. This is the definition from the book. The sum of two m times n matrices. Hey guys, m times n means rows times columns. There's different authors that use different letters for the matrix. In this book, they use m by n, which means m are the rows and n are the columns. Okay, so let me reread the definition. For matrix addition, the sum of the two m by n matrices x and y is a m by n matrix x plus y, in which each element is the sum of the corresponding elements of x and y. Hey guys, all this is saying, guys, is that say this is matrix A, matrix B, that you're gonna be adding the same position for every matrix. For example, A11 plus B11, A12 plus B12. That's what it means on the definition here. And same thing for subtraction. Okay, for subtraction, it's gonna be the same thing. It's gonna be A11 minus B11, A12 minus B12, and so forth. Okay. Now let's do examples with numbers. Okay, first of all, we have to know the size of the matrix. For example, matrix A is a 2 by 3. Matrix B is a 2 by 3. Matrix C is a 2 by 2, and matrix D is a 2 by 2. So then what's A plus B? First of all, can we add them? Sure we can, right? Because they're the same size. In order to add or subtract matrices, they have to be the same size. Both are 2 by 3s. So you see, so it's going to be 1 plus 8. Negative 3 plus 0. 2 plus 1, and then 2 plus negative 1, and 2 plus 3, and negative 1 plus 4. So then, right, 1 plus 8 will give us 9. Negative 3 plus 0 will give us negative 3. 2 plus 1 will give us 3. 2 plus negative 1 will give us 1. 2 plus 3 is 5. And negative 1 plus 4 will give us 3. Hey, students, you can go from here all the way to the answer. You don't have to put them like this, guys. This is just to show you how it's done. But you can go like this, guys, right? Say this is matrix A, matrix B. You can go 1 plus 8 is 9. Negative 3 plus 0 is negative 3, and so forth. You can do it that way. Okay, but I'm doing it this way just to show you what's taking place. Okay? Can we do C plus D? C is a 2 by 2, and D is a 2 by 2, so this can be done. So it's going to be 5 plus 2, 1 plus negative 1, negative 4 plus 9, and 3 plus negative 7. And here are the results. It will be 7, 0, 5, and negative 4. That's my answer for the matrix C plus D. Can we do A plus C? Matrix A plus matrix C. Not possible. Why? Because matrix A is a 2 by 3 and matrix C is a 2 by 2. These are not the same size of matrix, so that cannot be done. So not possible. Not the same size, okay? Now subtraction. Same thing as before. We use the same matrices as before, but now instead of adding, we're going to be subtracting. A minus B. So it's going to be 1 minus 8, negative 3 minus 0, 2 minus 1, 2 minus negative 1, 2 minus 3, negative 1 minus 4. So here are my solutions, right? 1 minus 8 will give us negative 7. Negative 3 minus 0 will give us negative 3. 2 minus 1 will be 1. 2 minus negative 1 will give us a positive 3. 2 minus 3 will give us negative 1. And negative 1 minus 4 will be negative 5. So that's my solution for A minus B. Now let's see C minus D. So 5 minus 2, 1 minus negative 1, negative 4 minus 9, and 3 minus negative 7. So this will be 3, 2, negative 13, and negative 10. So that's my solution for C minus D. Can we do A minus C? Right? A is a 2 by 3 and C is a 2 by 2. So it's not possible. Again, not the same size. Okay, now, this is called a scalar multiplication. The scalar multiplication, the product of a scalar K and a matrix X is a matrix Kx, which means that I'm going to multiply K times every element in X. Example, find 6X. So it's going to be 6 times, right? 6 times every element in X. So it'll be 6 times 2, 6 times 0, 6 times 5, 6 times 4, 6 times negative 2, and 6 times negative 3. So it's going to give us 12, 0, 30, 24, negative 12, and negative 18. That's the result of the scalar 6 times matrix X. Find negative X. Negative X is the same thing as negative 1 times matrix X, right? So are we just going to multiply negative 1 times every element in the matrix? So negative 1 times 2 is negative 2. Negative 1 times 0 will give us 0. Negative 1 times 5 will give us negative 5. Negative 1 times 4 will give us negative 4. Negative 1 times negative 2 will give us a positive 2. And negative 1 times negative 3 will give us a positive 3. Hey guys, if you notice, if you have negative X, that means that if there's no number here, right, it's like an invisible 1 there, right? But there's a 1 there. We can do this, guys. We can switch all the signs of the matrix. Of the elements in the matrix. For example, the 2 becomes negative 2. 0 stays as 0. The 5 becomes negative 5. the 4 becomes negative 4, the negative 2 becomes positive 2, and the negative 3 becomes positive 3. That's good to know, because when you subtract a matrix, you can actually turn it to addition, and this just switch all the signs on the negative matrix. Okay. Example 6. For 1, we're gonna do negative 4a. For 2, we're gonna do 5b. Then for 3, we're gonna add negative 4a plus 5b. Okay, so here we go. Negative 4 times a will give us negative 4 times the matrix a, which is negative 2, 0, 5, and 3. So it's gonna give us negative 4 times negative 2, negative 4 times 0, negative 4 times 5, and negative 4 times 3. Now, this step in the middle can be skipped, right? You can skip this step if you want, because it's kind of obvious that we multiply negative 4 times negative 2 will give us a positive 8. A negative 4 times 0 will give us a 0. Negative 4 times 5 will give us a negative 20. And negative 4 times 3 will give us a negative 12. So that's the solution for the matrix negative 4 times a. Now comes the second part, 5b. So 5b is the same thing as 5 times every element in matrix B. So 5 times 0, 5 times 2, 5 times 4, and 5 times negative 6. Right, so it's going to give us 0, 10, 20, and negative 30. So that's the result for the scalar 5 times matrix B. Now, negative 4 plus 5b, right? So, I mean, we already have the answer for negative 4. And we already have the answer for 5b, so let's just put them together. So this is negative 4a, right? That's why I color-coded in blue. Plus 5b, the answer for 5b is in red. Now we do what we did earlier, right? We're going to add them. So it's going to be 8 plus 0, 0 plus 10, negative 20 plus 20, and negative 12 plus negative 30. So my result will be 8, 10, 0, and negative 42. This is a result of negative 4 times matrix A plus 5 times matrix B. The result will be 8, 10, 0, negative 42. Okay, now let me go back here. Okay, now, hey guys, remember the example that we did at the beginning, right? To show you the concept. So again, all this here, guys, comes from the example from before. But the only difference is that we're going to let matrix C stand for Chicago, for the Chicago shipments. Okay, it says now, during August, the Chicago warehouse of Easy Company shipped out the following numbers of each model, which the entries in the matrix have the same meaning as given earlier. So it's going to be 5, right? It's going to be 5 models, 5 Model A sofas, 10 Model B sofas, and 3 Model C sofas, right? These are going to be shipped out. Then we have 13 for the chairs for Model A, 12 for Model B, and 8 for Model C. So how can we express that or show that in matrix form? What was the Chicago's warehouse inventory at the end of September? Take into account only the number of items received and sent out for the month. So these were received, and C was received, right, for the Chicago, and K was shipped out. So what was the inventory afterwards? So we're going to do C minus K. So C minus K is going to be matrix C, right, which is the one up here, minus the K, the material that got shipped out. So 10 minus 5 is 5, 12 minus 10 is 2, 5 minus 3 is 2, 15 minus 13 is 2, 20 minus 12 is 8, and 8 minus 8 is 0. So this is a result that's left after these got shipped out, which was represented by K. So this is the items left over. Okay, this is how you can apply it like in real life. Okay, now matrix product. We're going to multiply matrices. Okay, now this is very important here, guys. Okay, Multiplication on matrices can only be done under the following conditions. Say that matrix A, right, the size is n by n. And matrix B, it has to be n by something, right? Because the two numbers in the middle must match. So you put the size of the matrix of matrix A, or the first matrix, and then you put the size of the second matrix, right? The one that's being multiplied to A here, and then the two numbers in the middle must match. If they match, yes, it can be done. And if not, it cannot be done. But if it can be done, right, if they match, then the answer will be, the other ones will be an n by p matrix. Okay? If the size of the matrix is 2 by 3, then matrix B must be a 3 by something. Has to be a 3 by something. Right? This one doesn't matter. It can be a 3 by 1, a 3 by 2, a 3 by 3. This number here doesn't matter. What matters is the inner numbers must match. Okay, this is my rows, right? My columns. So the columns on the first matrix must match the rows on my second matrix. Okay. So the solution will be a 2 by something matrix, right? It depends what that number is. Okay, now, example 7. Given the following matrices. Okay, hold on, guys. Given the following matrices, state whether the matrix can be multiplied. Okay, first of all, to see, guys, right, so we have to write the order or the size of matrix A. Matrix A, okay, let's, no, we have to have a C. Matrix A is a 2 by 3. Matrix B is a 2 by 2. And matrix C is a 3 by 2. Okay, now, can we multiply A times B? Can we multiply B times A? Can we multiply A times C? Well, let's find out. A is a 2 by 3 matrix, and B is a 2 by 2 matrix. Can we multiply them? No, no match. So AB is not possible. Okay, let's try the B times A. So B is 2 by 2, and A is 2 by 3. Right, this is a match, so yes, it can be done. And the answer will be a 2 by 3 matrix. Let's see if we can multiply A times C. A is 2 by 3, and C is 3 by 2. And again, the inner numbers match, so yes, we can do the operation, and the answer will be a 2 by 2. Okay, so let's do them then. Okay, these were the ones that could be done. So here's how you do it. We have matrix A, matrix B times A, right? So it's a match. The answer will be a 2 by 3. So here's where we start. Step 1. Hey guys, in class, for the students that are taking my lecture class, I do a little bit different. But this is the way it should be done according to the book. Okay? But if you want to keep it my way, I mean, the way I show it to you guys, it's up to you guys, but this is the way the book explains it. Okay, now, right? Step 1, right? So this is B, matrix B, right? Is B times A, matrix B times matrix A. So I'm going to multiply the first row on matrix B times every column on matrix A. Okay? So I'm going to multiply first times first, which is 1 times 2. Then I'm going to add it to second times second to 0 plus 0 times 4. So 1 times 2 is 2, 0 times 4 is 0, 2 plus 0 will give us 2. That's your first entry on the 2 by 3 matrix. Step 2. Okay? Step 2. So step 2, right now, I'm going to multiply again the first row, but now times the second column. You see, the ones that we're multiplying are highlighted in blue and red. So now I'm going to multiply the first row times the second column. 1 times 0, 0 times negative 2. This is going to give us 0 plus 0 equals 0. So that becomes my next entry, which is 0. Step 3. I'm going to multiply again the 1, 0, but now times the last column, right, which is in red. So 1 times 5 plus 0 times negative 3 is going to give us 5 plus 0. The answer is 5. So that's my third entry on the first row. Now, right, since we're done with our first row times every column, now we do the second row. And that's why the second row is now in blue. And we repeat the same process as we did at the beginning. So now I'm going to multiply 4 times 2 plus negative 2 times 4. It's going to give us 8 minus 8, so the answer is 0. That the next entry on the matrix. Step 5 is going to be the second row times the second column. So 4 times 0 and negative 2 times negative 2. The answer will be 0 plus 4. The answer is 4. So that's the answer for the fifth entry here. Right? What's the location? This location will be the second row, second column. Now comes the last step. How do we know it's the last step? Because there's no more rows to multiply, and there's no more columns, guys. So this will be my last column, which will be the third column. 4 times 5, negative 2 times negative 3. 20 plus 6, the answer is 26. So this is my solution, guys. Here's my solution. 205, 0, 4, 26. That's how you multiply matrices. Okay, now, this is called the identity matrix. Recall from section 1.1 that a real number 1 is the identity element for multiplication of real numbers. For any real number a, if you multiply a times 1, it's the same thing as 1 times a, which is equal to a. In other words, if you multiply any number times 1, the answer will be that same number. And in a similar fashion, the identity for the matrix is denoted by I. I is the identity. And it has a similar properties. For example, matrix A times the identity is equal to the identity times A is equal to A. But the identity must be a square matrix, right? It can be a 1 by 1 matrix, a 2 by 2, or a 3 by 3, etc. It has to be a square matrix, which means the rows and the columns are the same. That's when you use the identity. Okay? Example 9. Matrix A is A, B, C, D, right? This is to prove it in general, that this is true. The identity matrix, right, if it's a 2 by 2, it's going to be 1, 0, 0, 1. Because if you notice, guys, for the identity, all the diagonals from left to right are equal to 1. You see, for the 2 by 2 matrix and for the 3 by 3 matrix, all these are 1s and the rest are 0s. So the identity matrix for a 2 by 2 matrix is 1, 0, 0, 1. Now find A times the identity, right? So it can be done. So again, right, so this is matrix A, and this is the identity. We're going to do the same thing as before for multiplication. So we're going to multiply A times 1 and add it to B times 0. Right? A times 1 is A, B times 0 is 0, so the answer will be A. That's my first entry. Step 2. I'm going to multiply the first row times the second column now, right? The second column. So A times 0 plus B times 1. The answer will be 0 plus B. The answer is B. Right? Then the third step. Step 3 right now, I'm going to switch rows now because I already multiplied the row 1 every column. Since there's no more columns to multiply by, then I switch to the second row times the first column. So C times 1 is C. D times 0 is 0. So C times 1 plus D times 0, the answer will be C. So that's my third entry. And finally, step 4. Right, so I'm going to multiply the second row times the second column. So C times 0 plus D times 1. The answer will be 0 plus D. The answer is D. You see, guys, we get the same thing. So any matrix times its identity, the answer will be the very same matrix. That's what I'm trying to show here, guys. Okay, and I believe on your homework for my math lab, I believe you have something like that. So if you have any matrix times its identity, you don't even have to do the multiplication. It will just be the very same matrix. Okay. Okay, now inverse matrix. Recall that for every non-zero real number a, the equation ax equals to 1 has a solution. Namely, right, x equals to 1 divided by a, which is the inverse. A to a negative 1 is the inverse. Similar for a square matrix. A, we consider the matrix equations ax equals to I, which is the identity. The equation does not always have a solution, but when it does, we have a special terminology. If there is a matrix that has an inverse, then the original matrix A times its inverse must equal to the identity. A to a negative 1 is called the inverse matrix. Okay? So example number 10. It's always better when you do examples because at times the vocabulary or the definitions at times they're kind of hard to understand. And that's why, but this is a concept here. Now I'm going to show you by examples, okay, with numbers. Example 10, given matrix A and B as follows. Determine whether B is an inverse of A. Because for this to be inverse of each other, right, when I multiply them, it has to give me the identity, which will be the 1, 0, 0, 1 matrix. So if I multiply these guys, it is going to give me the 1, 0, 0, 1 matrix. So that means these two are inverse of each other, right, which is equal to I. B is the inverse of A because A times B equals to the identity. Okay, guys, and I didn't want to actually multiply it out because I have this PowerPoint is about, I'll be running a little bit late if I actually do all the work, but just follow the steps from before and you'll be able to get it. Okay. Okay, now, if matrix A has an inverse, then A, right, A and the identity must equal to the inverse. So how do we do that? Remember, guys, the Gauss-Jordan method that we did last week? We're going to do it again now. You see, guys, this is matrix A, and this is its identity. So this is a plan now. I need to make the 1, 0, 0, 1 come to the left side. And whatever's left on the right side, that'll be its inverse. You see, use Gauss-Jordan method from 6.2. You see, so this is my inverse. Okay. Now, how are we going to do that? Let me show you how on the next slide. Okay. Hey guys, recall from the past. These right here, the first step, there has to be a 0 there. This is row 1. This is row 2. So I'm going to multiply negative 2 row 1 and add it to row 2. Why? Because I want this to be a 0, right? In other words, I want the identity to come to the left, and whatever's on the right will be the inverse. Right, so the first row stays the same. Now here's my work. Negative 2 row 1 is equal to negative 2, right, times row 1. This is my row 1 here. So it's going to give us negative 2. Negative 2 times 4 is negative 8. Negative 2 times 1 is negative 2. And negative 2 times 0 will give us 0. Then add it to row 2. Row 2 is 2, 6, 0, 1. So if I add them, it's going to give me 0, negative 2, and 1. So this is my new row 2. Now, we're done with the first part here, guys. Now, my second part, this has to be a 0 there, right? That has to be a 0. So I'm going to be using row 2, which means row 1's got to change, right? There has to be a 0. Where the 4 is, it's got to be a 0. So I'm going to multiply 2 times row 2 and add it to row 1. Right? And my row 2 stays the same because I'm going to be using row 2. So here's my work here. 2 row 2 plus row 1. Okay, so 2 row 2 will give us 2 times 0, negative 2, and 1, right? I got that from here. This is my row 2 here. So it's going to give us 0. 2 times negative 2 is negative 4. 2 times negative 2 is negative 4. And 2 times 1 will give us 2. Now I need to add it to row 1. Row 1, right, is 1, 4, 1, 0. 1, 4, 1, 0. So after we do the operation, it's going to give us 1, 0, negative 3, 2. That's my new row 1. If you notice, we're almost done here. Now this has to be a 1 here now, right? Right, and we'll be done. So I'm going to multiply row 2 by negative 1/2. So it'll be negative 1/2 row 2. Right? So negative 1/2 times 0 will give me 0. Negative 1/2 times negative 2 will give us a positive 1. Negative 1/2 times negative 2 will give me a positive 1. And negative 1/2 times 1 will give me negative 1/2. So this is my inverse. That's my answer, guys. Okay, now, there's another way to find the inverse of a 2 by 2 matrix. It only works for a 2 by 2 matrix, not for anything else, only a 2 by 2. Okay, let me show you the formula here, guys. Formula to find the inverse of a 2 by 2 matrix. So this is my formula. Say you have matrix A, right? You want to get the inverse. The inverse is equal to 1 over, you're going to multiply A times D minus B times C. And then these two, the A and the D matrix, the A and the D elements, you switch them. D goes there and A goes here. And for the B and C, all you do is switch the signs. Okay? We switch the signs. Okay, again. Hey guys, the A times D minus B times C is also called the determinant. Okay? So example 11, find the inverse of a matrix A. Okay? So what's my inverse? I believe it's the same matrix as before. So it's going to be 1 over 1 times 6 minus 4 times 2. And then the one in the right, the one in the 6, we switch them. 6 goes here and 1 goes there. And for the B and the C, which is the 4 and the 2, all we do is switch the signs. Okay, that's how you apply the formula for the inverse of a 2 by 2 matrix. So then this will be 6 minus 8, so it will be negative 1/2. Then you have to multiply negative 1/2 times every element in the matrix. So negative 1/2 times 6, right, will give us 3. Negative 1/2 times negative 4 will give us positive 2. Negative 1/2 times negative 2 will give us a positive 1. And negative 1/2 times 1 will give us a negative 1/2. So this is my inverse. You see, same thing as before, guys. But I believe this is easier to use for the students. Because today during class, I did them both ways, and the students mentioned that they like this formula better. Okay, but it all depends on your instructor. At times, the instructor might say, find the inverse by using the Gauss-Jordan method. So you have to do it the other way, the example I showed on the previous slide. Or they tell you to use a formula, then you use this one. But if they don't give it, if they're not specific what to use, you use whatever's better for you, for which method you understand better. Okay? Now, for a 3 by 3 matrix, it's not that easy, guys. This is as hard as it gets. Okay, because there's no easy way to do it with a 3 by 3 matrix. So for the inverse of a 3 by 3, I'm going to put the augmented form of matrix A with the identity matrix here. Okay, now, in similar fashion, I need to make the identity come to the left, and then whatever's left on the right, after the identity matrix comes to the left, then this will be my inverse. Okay, we have to use the Gauss-Jordan method from 6.2. It's what I covered last week on the PowerPoint last week. Okay, now I'm not going to go too much in detail, guys, as I did last week, but I'm going to show you all the steps. Okay, guys, this should be my inverse here. This is my inverse. Right? This is your inverse on the left. On the right, I mean. Okay, now, how are we going to do it? Here's how. Right? So we put them, this is row 1, row 2, row 3. Because remember from last week, this is row 1. The 2 and the 5 must be zeros. These two must be zeros here. So I'm going to use row 1. So anyway, row 1 stays the same because that's the one I'm going to use. The second row must change, right? Because the 2 must be a 0, and the third row must also change because the 5 must be a 0. So I'm going to multiply negative 2 times row 1 and add it to row 2. Then I'm going to multiply negative 5 times row 1 and add it to row 3. And here's my work. The step 1 has 2 parts, A and B, right? So negative 2 row 1 equals to negative 2, right, times row 1. Which will give us negative 2, 0, negative 2, negative 2, 0, 0. And then plus row 2. Row 2, right, will be 2, negative 2, 1, negative 1, 0, 1, 0. And after we add them, it's going to give us 0, negative 2, negative 3, negative 2, 1, 0. So that's my new row 2. Now I'm going to multiply negative 5 row 1, right? So negative 5 row 1 is negative 5 times this is row 1 here. So after I distribute, it's going to give us negative 5, 0, negative 5, negative 5, 0, and 0. I'm going to add it to row 3, right? So row 3 is 5, 0, 0, 0, 0, 1. So after we add them, it's going to give us 0, 0, negative 5, negative 5, 0, 1. So this is my new row 3. Now, if you notice, for step 2, right, step 2 is already done because for step 2, these two must be zeros, as I mentioned last week. So step 2 is already done. So now we do step 3 then. Step 3, these two must be zeros, right? These two here must be zeros. So I'm going to keep row 3. So I'm going to change row 1 and row 2. So I'm going to multiply, I'm going to add row 3 plus 5 row 1, right? Because row 3 so it's okay, but I need to multiply 5 times 1 to give me a positive 5. Then when I add them, there'll be a 0 there. So for row 2, I'm going to multiply, because they're both negative, I need to multiply negative 3 times row 3 and add it to 5 times row 2. And here's my work over here on this side. So right, so row 3 plus 5 row 1, right? So this is 5 and this is my row 1 here. The 1, 0, 1, 1, 0, 0. I got it from here. So after I distribute, it's going to give us 5, 0, 5, 5, 0, 0, 0. After we do the operation, it's going to give us 5, 0, 0, 0, 0, 1. So that's my new row 1. Now for row 2, right? The negative 3 row 3 is negative 3 times row 3. This is my row 3 here, right? That's what I have here. So it's going to give us 0, 0, 15, 15, 0, negative 3. Then when I add it to 5 row 2, right? So 5 times row 2 is going to be 5 times row 2, which will give us 0, negative 10, negative 15, negative 10, 5, and 0. So that's my new row 2. Now, but remember, right? We're almost done here, but the ones here diagonally must be ones. So then that's going to change, right? Because that's going to be a 1. The negative 10 has to be a 1, and the negative 5 has to be a 1. How are we going to do it? So I'm going to multiply 1/5 times row 1, because 1/5 times 5 will give me a 1. But I need to multiply it times every element here. So 1/5 times 5 will give us a 1. 1/5 times 0 will give us 0. 1/5 times 0 will give me 0. And 1/5 times 0 will give me 0. And also here 0. But here is going to be 1/5. Now for row 2, I need to multiply negative 1 over 10 times row 2. If I do that, this will be my solution here, guys. In a similar fashion, I need to multiply negative 1/5 times row 3. So after I multiply 1/5 times every element, it's going to give us 0, 0, 1, 1, 0, 5, negative 1/5. So this is my, let me go back. Hey guys, so this here, guys, is my inverse, right? Just what I had before on the previous slide. So that's my solution. And I believe that's it for today's PowerPoint. I hope that you understood it. Does anybody have any questions? Questions, anyone? Okay, so I guess I'm gonna stop sharing my screen so I can go back to the original Blackboard site. So if there's no more questions, guys, or any questions at all, I want to thank you for joining my our Friday happy hour, math happy hour, and hopefully this material is useful for your classes for the 0324 and 1324.
Thank you, Mr. Azasi. Thank you, everyone, for coming today. Oh, Brenda says she understands it a bit better. So that's awesome, Brenda. I'm glad to hear it. Make sure that y'all please sign in today. There's a link in the chat along with the code word HOPE. So please click that link and sign in for us. Also, I'd like to invite y'all to next week's Happy Math Hour for Math 1314. They'll be going over linear and nonlinear systems. And for Math 1324, we'll be going over the review for Exam 3. Again, I'd like to thank Mr. Azasi, and I'd like to thank everyone for being here today. I hope you all have a wonderful weekend, and happy April Fools.
Thank you, Patricia.